Okay, now for backward Euler, we discussed that it leads to a nonlinear differential equation, and after we convert it into a discretized equation, the set of equations still is nonlinear. So we have to use Newton's method to solve this equation for theta I plus 1 and theta naught I plus 1. For Newton's method, we have to calculate the Jacobian. Now Jacobian is going to be the partial derivative of the first equation right here, and second equation with respect to the two unknowns. Okay, so the first equation is this one, and we get the derivative of that with respect to the first unknown, which is theta I plus 1 is going to be 1. Derivative of that with respect to theta dot I plus 1 is going to be minus delta t. Now go to the second row, the derivative of this with respect to theta I plus 1 is going to be minus cosine, well there's another minus here, so it's going to be plus cosine theta I plus 1 times delta t. Okay, derivative of this equation with respect to theta I plus 1 is going to be 1 here, that's right here, and then plus, so minus becomes plus delta t beta, and then we have derivative of this times that plus derivative of this times this. So we get 2 times theta dot I plus 1 absolute value, okay? Because the two terms are identical. Derivative of this times that is the same as the derivative of this times this. Okay, so that's how we get the Jacobian. Now we have to solve this iteratively. Then theta I plus 1, theta dot I plus 1 at iteration n plus 1 is going to be the same thing at iteration n minus Jacobian inverse, or in other words, back a slash. So it's going to be Jacobian back a slash, and then the right hand side, which is just the equation, the solved equation, right? So the first one is right here, and the second equation is right there. Okay, and so the way to update that is we cycle over different n values. For a given I, we cycle over different n's, right? Okay, so after we iterate this, then we can solve for theta I plus 1 and theta dot I plus 1, and then we can change I and go to the next I value. Okay, so and that's how we can iteratively solve for all the unknowns, the thetas and theta dots, okay, for different values of I. Now, because backward Euler was implicit method, we had to use Newton's method. Same thing with atom molten. In atom molten, it's still it's an implicit equation. So if we write the discretized equation, we're going to have an equation like this. Okay, where again yi is going to be y plus 1 is going to be a vector which includes theta I plus 1 and theta dot I plus 1. The rest of it is very similar to the backward Euler or forward Euler. We'll have to plug in the f at tyi and f at tyi plus 1. And by doing so, we get an equation like that, where it's involved with theta I plus 1, theta dot I, and theta dot I plus 1. Okay, now the goal again here is to solve for theta I plus 1 and theta dot I plus 1. We have to solve for the Jacobian, well, we have to get the Jacobian of this again, and then use the back a slash operator in iteration over different n values to solve for theta I plus 1 and theta dot I plus 1. So I don't go over the Jacobian, it's very similar to the backward Euler. The only thing is the equations are a little bit different, and so the Jacobian will be different. Okay, and let's see, so we already talked about the stability analysis. Now, in case if beta is 0, then we have to look at the Jacobian, the eigenvalues of the Jacobian, and the eigenvalues of the Jacobian will tell us whether the method is going to be stable or not. I think the rest of it we already talked about. The stability region for RQ2 and RQ4, I think I talked about it in in a video before, so make sure you watch it before you do the pendulum problem. Okay, so I think that ends the discussion on stability analysis and accuracy for the methods we covered so far: forward, backward Euler, RK214, and Adamot. So in the next video, we're going to focus on stiff problems, and I'll try to understand what stiff problems are. Just in short, stiff problems are the problems that involve with at least 2 different time scales, like one time scale is short, the other time scale is long, and if you want to really solve the whole problem with 2 different time scales, then the problem actually boils down into the delta t or delta x. If delta x or delta t is small, then of course we can resolve both time scales, but then that requires many iterations or many time steps. At the same time, if delta t is large, then there are not many time steps. However, the accuracy goes down because we had this condition for the stability in accuracy. So if delta t or delta x becomes really large, then the method can be unstable. So now we actually see this problem that we cannot do either method. I mean, we cannot do small delta t because it requires many time steps and the problem takes really long time to solve. At the same time, if delta t is large, we cannot even solve it again because the method becomes unstable. So that leads to the discussion of stiff ODEs, or stiff ordinary differential equations, and the associated techniques that we need to deal with, be able to solve the problems. Okay, so stay tuned and thanks for watching. In the next video, I'll be talking about stiff ODEs.